Let me start with my presentation for today. So hi everyone again, my name is Raj Dasgupta. Right now I'm with NRL, the Naval Research Lab. I've joined there about 4 months ago, and prior to that I used to be a faculty at U Nebraska, and that's where this work was done. So this is joint work with my graduate student Anup Mishra. My collaborators on this research were Carl Lenson from U Nebraska Lincoln and Judith Burnfield from Madonna Rehabilitation Center in Lincoln, Nebraska. Okay. And the topic of our paper is to build semi-autonomous intelligent control of a modular robot and apply it to human assistive tasks. This is the outline of my talk. So the main contribution of our research basically is in points 4 and 5, which is we've proposed a reinforcement learning, a type of machine learning algorithm for semi-autonomous control of the robot. And we integrate the machine learning algorithm with a human-robot interaction technique called Shear Autonomy. And much of the work, as you will see, is done on simulation right now. The hardware robot is currently being built, but most of what I'm going to report today is done with a simulated model of the hardware robot. So the problem, as I was just mentioning, is to assist patients who have limited mobility of their upper body. For example, patients who have spinal cord injury, build a robot that can help them perform assistive tasks. Now, of course, as we are all aware, there are several robots which perform this task already. But if you look at literature, if you look at the systems that are out there, most of these robots which perform assistive tasks for humans with limited mobility, they are essentially fixed configuration robots. What we are proposing here is, can we use a modular self-reconfigurable robot that can change its shape, change its configuration depending on the type of assistive task. So the robot that we propose is called Mario. So quick overview of what modular self-reconfigurable robots, or MSRs for short, are. Now MSRs have been around for nearly, I think in the early 90s is when they came about. So the main idea of MSRs is that they are composed of modules or blocks, and these modules can interconnect and disconnect with each other. Essentially, they can form several shapes or configurations. And the idea is that depending on the task at hand, these robots could reconfigure to the appropriate shape, to the most efficient shape or configuration, and also have an associated gate or technique by which they can move to perform the task. The advantage of using this modular self-reconfigurable robots is, of course, you can reconfigure them and you have the ability to reach tight spaces. Basically, they're highly dexterous robots. So at the bottom of the slide, I have given pictures of some of the modular robots that have been around. One on the far left is called Polybot. Then there's Mtran, the one with the blue background, Mtran 3. The one below that is called Atron. And Superbot is the one in the middle. And on the far right, we have a robot that we built in our lab back in 2009. That robot was called ModRed. The work I'm going to present today is built off, to some extent, from the hardware design of ModRed. Okay. So, the ModRed robot basically was, this is the ModRed robot, the second version of the ModRed robot. The objective of the ModRed robot was space applications. So essentially the idea was, if you send the robot to an extraterrestrial surface like the moon or Mars, there you do not have a map of the environment in which the robot is going to move. Basically, it's unstructured terrain. And so if you have a reconfigurable robot, then it can change its shape in real time and essentially move around. For example, if you have a wheeled robot, as you know, wheeled robots are not very good at climbing stairs. But if the robot could change shape and sort of go to a threaded structure, then it could be able to climb steps or go over rocks in the lunar surface. So that's the idea we had for space exploration. And then for this research, what we thought about was, apart from applying it to space exploration, how about we apply the self-reconfiguration property of the robot to perform human-assisted tasks? Okay. And this was, as far as we know, this was the first application of a self-reconfigurable robot for performing human-assisted tasks. Okay. So the robot that we have is called Mario. It stands for Modular Robot for Assistance in Robust and Intelligent Operations. And the idea is, as I was saying, to assist patients with limited upper body mobility performing daily living tasks. So our partners have been building the hardware of the robot, and also there's another partner who's at the hospital who's looking at how humans are able to use the robots, basically the human studies with the robot, how adaptable they are. So our portion in this research has been mainly on the software aspect, basically the intelligent semi-autonomous control, essentially focusing in this work on the navigation of the robot from the source location to a goal location to put the task and navigating back to the human. Okay. And the techniques that we use are machine learning, form of machine learning called reinforcement learning, integrate that with shared autonomy. So here's a video which highlights what we plan to achieve with this research. So I'll let it play. It's about a 2-minute or so video. So as I was saying, the main idea is this robot is able to reconfigure to perform the task at hand. And we plan to use it to perform assistive, like daily living tasks. So this is just a simulation inside the kitchen environment, it's a simulation of the robot. So basically it can be used to reach faraway objects, which human probably cannot stand up and reach. And it can be used to perform different tasks. So here it's shown to reach the cabinet door. And the same robot can be used to also like reach over and open a kitchen faucet, for example. And then it could also be used to like lift things off the floor. For example, if the patient drops a plate or drops a TV remote, for example, or needs to fetch a pillow from the floor, that could also be used. Basically, you can do things like this, move objects around with the robot. So let me pause this, and I have some more of these videos towards the end of my presentation. But okay. So I've already talked about it. So the first aspect of our research that we looked at was we explored by hand which configurations of the robot would be effective in performing the task at hand. So we are showing several configurations of the robot out here. So on the bottom left, we show a H-shaped configuration, like it can, the two sides of the robot can move like a wheel, and it can sort of take two objects on it. In the middle, you're seeing a pie-shaped configuration that's less stable than the H-shaped configuration, but still it's more lightweight, so it can move faster and with less energy. And a couple of more few other configurations, like the L-shaped configuration. It's much lighter weight, just 3 modules there, but the object, while turning, the object can slip outside. So there are pros and cons. You trade stability for lightweight, for time, and so on. So we looked at these, and then we looked at what are the type of tasks, very basic tasks that we could have this robot perform. So this is a very fundamental task we are having the robot, which is we put the robot in a certain shape or configuration, and we ask it to navigate from a source location to the location of the task. We give it the location of the task, and once it goes to the task, and the task can be like trying to grab a basket of fruits, and then go to the location of the task, perform the task, which is basically grasping or grabbing, and bring the object back to where the human user is. So here we are looking at how the robot can do, how we can do navigation control of the robot. Basically move the different joints and motors of the robot to make it go to the task's location, to the goal location. So the problem with this is the state space and the action space of the robot is very large. So what we are using is a technique called reinforcement learning, which has been used recently quite a lot for navigation of robots, essentially high degree of freedom robots. And basically with reinforcement learning, we are using a deep neural network here. So basically with reinforcement learning, the general idea is the robot has different actions that it can take. And basically it goes through, in simulation, it explores the different actions and sees which actions correspond to higher reward. And so later on when the robot is deployed, it tries to choose the high reward action. Of course, there's a trade-off between exploitation and exploration, and that's integrated into the model. But the essential idea is you try out different actions and see which actions lead to higher reward, and then you reuse those actions. Okay. So we used a type of reinforcement learning called actor-critic learning, and within that we used a recent algorithm called DDP, Deep Deterministic Policy Gradient. Performed some experiments. Basically we gave it different tasks. In some of the tasks the robot needed to either turn left or turn right from the source location, and also the length or the distance that the robot would have to travel. We changed that from between 1.1 meter in tasks 4 and 5 to about 11 meter, 13 meter, and so on. So we compared the effect of the reinforcement learning algorithm with a purely reactive controller, where the reactive controller was just trying to adjust the motion of the robot based on how much it moved away from its optimal path due to noise or so. And we saw that the reinforcement learning technique was able to do the operation in much lesser time. In the second step, what we did was we combined this reinforcement learning with shared autonomy. So the idea is ultimately we want the robot to work with a human, and so satisfaction of the human, improving the trust of the human in using the robot is one of the main issues that we wanted to handle. So in shared autonomy, what happens is if the human sometimes sees the robot and feels that the robot is not doing the task like the human would want to do, the robot does the reinforcement learning, calculates the optimum policy and tries to execute the actions as per the policy. But the human might feel that that's not the best way I want to do it. Sometimes the human might be able to do it in a more optimal way. Sometimes the human might be suboptimal. For example, the robot, using its machine learning, figures out that the best way for me to grab an object is to approach it from its front. But the humans might feel that, no, I want to see what the robot is doing. So I want the robot to go around the object, go from the back of the object and grasp it. So in that case, the human would want to override the robot, although the human might be suboptimal. In other cases, the robot might be suboptimal. For example, due to slippage or due to friction in the surface, the robot might be deviating from its optimal path. Human observes that and tries to control the robot via joystick or something and bring it back to its optimal path. So there can be both aspects of shared autonomy. Shared autonomy is not fixed. The idea is shared. So basically when the robot tries to do its optimal policy, and when it sees that the human is trying to override, it sort of gives a weight between what its optimal algorithm is telling and what the human does. And if the human repeatedly tells the robot to deviate from its optimal path, then ultimately the human's action takes precedence. So here are some videos, but for the sake of time, I will skip ahead of that. And basically the graphs there show that when I have combined shared autonomy, as opposed to not having shared autonomy, I can do the tasks in less time. And in this case, the human saw that the robot was slipping, probably deviating from its optimal path, and the human sort of overrid the action of the robot and said that this is the more optimal way to do the path and able to save time. Of course, it's felt more when the distance between the tasks is higher, in tasks 1 to 3 as opposed to 5. Okay, so I'm almost nearing time, so I will just wrap up saying that this was just scratching the surface. So we tried to integrate reinforcement learning and shared autonomy, and to the best of the literature review that we did, to the best of our knowledge, we believe this is the first time that reinforcement learning and shared autonomy is being applied to a self-reconfigurable robot and applying that to assistive tasks, to the theme of this symposium, Do Good Robotics. And so basically these were the 3 steps: finding out configurations, applying deep reinforcement learning, and combining deep reinforcement learning with shared autonomy. In the future, we plan to take this to hardware experiments and look at more complex tasks. So that's my talk. Thank you.
Questions for Dr. Dasgupta? Yes.
So I had a question with the shared autonomy part. How are the robot and the human communicating? What is the form of communication that happens between them?
So, as regards the hardware aspect, the human is the joystick.
Okay.
With which, so I was just saying that as regards the hardware aspect, the human is a joystick, and there's wireless control available on the robot. So right now we are doing this in simulation. So in the simulator, what we have is we have a mouse, and with the mouse, when the human clicks the mouse, basically the left mouse corresponds to turn left, right mouse corresponds to turn right, double click corresponds to keep going straight. So in that way, we are giving sort of simulating the joystick movement. If you're asking about the software aspect, so basically the human and the robot, they basically share an MDP. It's a type of MDP called MOMDP, multi-objective Markov decisions. So that's a software, or that's the math framework that's used internally, MOMDP. Okay. Any more questions?
Any other questions?
So, just like a curious question, since you're using deep reinforcement learning, so I just wanted to know what were the challenges which you faced while using deep reinforcement for learning, and did you see some failure cases?
In fact, we saw many failure cases.
Actually, the question that you asked is a good one, because we saw several issues, several cases where the robot would not work as expected. Basically, with fixed configuration robots, it's much easier to do. As soon as you're looking at self-reconfigurable robot, basically when we are trying to actuate the robot in a certain way, the software algorithm says that do this action, but when we try to implement it in our hardware, the joints somehow snap, because you can take apart the blocks, the modules of the self-reconfigurable. When you try to actuate at a certain speed to do that action, the robot basically snaps and comes apart. So basically there's a trade-off that we saw. So although the software algorithm might say do this action, translating the action to hardware was sort of the hardest part that we saw.
And were you able to hypothesize that why the system works the way it is expected, or the way you observe it through the...
Basically, the problem is that the state space and action spaces are very large. So if you try to do any other form of learning, like supervised learning and so on, so it would not work, because there are so many cases you would not be able to give enough training data, or the training would take too much time. So with reinforcement learning, basically you can explore the space, and prior to the working of the loop, prior to the real time, you can sort of explore and sort of keep a balance between explore and exploit. Also, there is some stochasticity built in there, because the robot can slip, and there's slippage. So basically reinforcement learning, due to the balancing it does between explore and exploit, helps to address that issue. I think since I'm the session chair also, I'm looking at the time, and I'm seeing it's almost 20 minutes. So,
how is it a trade-off between exploitation and exploration?
Okay, so to answer that, I might want to take that offline, because the reinforcement learning algorithm that is there, the output of that is a policy. Policy basically is a mapping from state to action, and there's some stochasticity built into that. So always you will not do the optimal policy. With some probability you will do the optimal policy, but with some other probability, like one minus that probability, you will do an explore action. So that's how it balances explore and exploit. So that has to do with the technique of the reinforcement learning.